In this video, I'm going to show you how to use a method called the second derivative test. Now, sometimes concavity can provide a way to tell whether a critical point is a maximum or a minimum. So when we do this, this method is called the second derivative test. Now, consider a critical point where the first derivative is equal to 0. So this is where the tangent line is going to be horizontal. So here's two possibilities. One at point A on this graph, and one at point B in the second graph. So the point A, we can see, is a local max. It occurs at a place where the curve is concave down. So that means our second derivative is less than 0. Now the point B is a local minimum. So it occurs at a place where the curve is now concave up. So therefore, our second derivative is greater than 0. So to summarize, suppose f double prime, or the second derivative, is continuous near a point C. If the first derivative is equal to 0, and the second derivative is greater than 0, then we say that f has a local minimum at C. If the first derivative is equal to 0 and the second derivative is less than 0, then f has a local maximum at C. So think of it this way. When it's greater, everything is above it. So the graph is above it, so we have a minimum. When the second derivative is less than 0, think of the graph is below that point, and so it has a local max. Now, if the second derivative test equals 0, it doesn't mean that we actually know anything that happens. We say that the test fails. So f may have a maximum, a minimum, or neither. So this test also fails when f double prime, or the second derivative, does not exist. So when this happens, we now need to use the first derivative test to figure out whether this point is a local maximum or minimum. So let's take a look at a couple of examples. So in this first one here, we have f of x equal to x divided by 1 plus x squared. So we need to find our first derivative, and we need to use the quotient rule since we have a division here. So the derivative of x is 1 times 1 plus x squared minus our numerator times the derivative of our denominator, which is 2x. And then all of this is going to be divided by 1 plus x squared, all squared. Let's do a bit of simplifying. So we have 1 plus x squared minus 2x squared, all divided by our denominator. So we have 1 minus x squared, all divided by 1 plus x squared, squared. Set this equal to 0. So really we are only concerned with our numerator. And then we have x squared equals 1. So x equals plus or minus 1. Now we should also check to see where our denominator is undefined. So we have 1 plus x squared equals 0. So x squared equals negative 1. So there is no place that this happens. So here, there is no solution. So the only place we need to check is where x is equal to plus or minus 1. All right. Now, before we do that, the second derivative test states that we also must find the second derivative. So we're going to use this function here for our first derivative, and we're going to find the second derivative based on that. So we have negative 2x, which is the derivative of our numerator, times 1 plus x squared, squared, minus our numerator, times our denominator, or the derivative of our denominator. So this will be 2 times 1 plus x squared, which is now to the power of 1. And now we need to use the chain rule to do the derivative of the inside, which will be 2x. And then all of this will be divided by 1 plus x squared, now to the power of 4. Okay, definitely we want to do some simplifying here. Now, one thing that I do notice is that in my numerator, I have a 1 plus x squared in both, and I also have a 2 in both. So what I'm going to do is I'm going to factor this out. Oh, actually a 2x. So I'm going to factor out a negative 2x and a 1 plus x squared. So I still have a 1 plus x squared minus, and then so this is factored out, and this is factored out, and so is the minus sign. So I'm going to have plus, and I'm going to distribute this inside to here. So I have 2 minus 2x squared. So actually I don't need this bracket here. And then all of this will be divided by 1 plus x squared to the power of 4. So let's continue to do a little bit of simplifying before I do some plugging in. I see that there's one of those at the top, so this is going to be 3. So now I have negative 2x, and 1 plus 2 is 3, and then I have plus x squared minus 2x squared, so I have negative x squared. And then all divided by 1 plus x squared, now to the power of 3. All right, so I'm going to now plug in these numbers I got from the first derivative. X is 1 and negative 1. So when I plug in negative 1, I'm going to have, sorry, I get 2, 3 minus 1, negative 1, so squared, 1 plus 1 is 2, 2 cubed is 8. Excuse me. So I get 4, 8's on the top, which is greater than 0. Okay, so therefore, I have a local min at x equal to negative 1, and that min is equal to negative 1, and I want to find out, if I want to find out what the y value, don't forget that the minimum is actually plugging negative 1 into my original function back up here. Okay, so actually I'm going to rewrite this like this so that I can show you that the local min is equal to negative a half. All right, so now let's plug in 1. And I get negative 4/8, which is less than 0. So that means that I get a local max at x equals 1. And that local max value is equal to a half. All right, let's show you one more example. So let's find the first derivative. So f prime of x equals x cubed minus 6x squared, and set this equal to 0, and I'm going to do some factoring. I'm going to factor out an x squared, so I have x minus 6. So here x equals 0 and 6. This is a nicer one to find the second derivative, not like that quotient one we have. So the second derivative is equal to 3x squared minus 12x. And now we're going to plug in these two values. So f double prime of 0. When I plug this in, I get 0. So this is actually inconclusive, remember? It doesn't mean that we don't know what's happening. We just don't, the test fails. So therefore, for this one, I need to use the first derivative test. Okay, so I'm going to come back to that one. Actually, you know what? Let's do this now since we're already here. So we're going to, remember how this works. We plot 0, and we're going to test a number on either side of 0. So let's say we have an f prime of negative 1 and f prime of 1. So when I put in negative 1 into here, sorry, I get negative, which means is going down. and I plug in 1, it's also negative, and it's going down. So that means there's actually no extreme value at 0 because it's going down and then down again. So no extreme value at x equals 0. Let's now test our second number, which is 6. And when I do that, I get 3 times 6 squared minus 12 times 6. And I get 36, which is greater than 0. So therefore, for this one, I know that I have a local minimum at x equals 6. And that minimum value is equal to negative 102. Now, just to kind of reiterate, it is not true that if f or the first derivative equals 0, it is a critical point, and then f double prime or the second derivative equals 0, so the second derivative test fails. Then because this is equal to 0 and the second derivative also equals 0, it doesn't mean that we don't have a max nor a min. It just means that the test fails and you can draw no conclusion, so you need to do some more work. So the point could still be a max or min. So what we need to then do is to use our first derivative test to do some more testing. So for example, consider y equals x to the power of 4. When I take the first derivative, I get 4x cubed. Take the second derivative, I get 12x squared. So y prime of 0 is equal to 0. And then y double prime of 0 also equals 0. Thus, we know that x is a critical point, and the second derivative test fails since the second derivative test equals 0. However, x equals 0 is actually a local min, as you can verify by using the first derivative test. And if you know anything about y equals x to the power of 4, this graph looks something like this. And we know that there has to be a minimum at 0 right at the origin here. And this concludes the second derivative test.